Greetings. Thank you for joining my presentation. My name is Nguyen. I am a postgraduate student in the School of Computer Science of the University of Adelaide. My research focuses on enabling a search engine for anything, at any place, and any time in the Web of Things. In this presentation, I will present a service-oriented, kernel-based solution to develop modular, extensible, and adaptable search engines for sensors and data streams in the Web of Things. The physical world, our world, is the final frontier of software applications. Traditionally, software applications rely on humans to gather information and interact with the physical world. However, feeding information into computers and following their calculated course of action are monotonous, which are more suitable for machines. By closing the loop between computers and the physical world via sensors and actuators, software applications can automate and optimize different activities in the physical world with higher efficiency, while leaving humans to focus on more creative and abstract tasks. In the past, to interact with the physical world, a software application must establish a static and closed coupling with a sensing and actuating infrastructure using proprietary protocols. The use of these protocols complicates the development of applications, while the closed coupling complicates the sharing of infrastructure. As a result, it is not cost-effective to develop these cyber-physical systems. The Web of Things is an emerging alternative, with the support of software systems called Web of Things middleware. Sensing and actuating infrastructures can be abstracted and served as web resources. Applications retrieve these resources using web protocols to implement the interaction with the physical world. The Web of Things allows sharing, sensing, and actuating infrastructures. It also simplifies the development of cyber-physical applications. When Web of Things resources are ubiquitously and massively available, the task of finding relevant, optimal, and safe resources for applications becomes a major challenge. A simple solution is linking applications to resources during design and deployment time. However, the resulting systems are static and closed, which are no different from solutions before the Web of Things. An alternative is developing a software system that is responsible for detecting and resolving queries on Web of Things resources. In the case of resources offered by sensors, we call these systems as Web Sensor Retrieval System. Developing web sensor retrieval systems is an extensive and diverse problem. First, the system must be able to process different forms of presentation utilized by sensors, data streams, and observations. Second, the system must be able to answer various forms of queries, such as spatial, temporal, semantic, as well as queries on sensing data and information derived from this data. This diversity introduces a dilemma between generality and specificity. A search engine is expected to answer any type of query for any class of sensors and data streams. However, a functional search engine requires a concrete set of algorithms and mechanisms for a specific type of query and sensor. So, how to create a functional search engine that can actually find any sensing resources. The solution that we propose is working together. It involves decomposing web sensor retrieval systems into well-defined components and facilitating their independent creation by different researchers and developers. Each component encapsulates a specific mechanism to process a specific class of sensors to answer a specific type of query. These components then integrated to form a functional search engine that satisfies the given query. Larger collection of components will allow composing more types of search engines. Eventually, we will have a functional web sensor retrieval system that can resolve queries for any sensor. Our solution can be realized in 3 steps. The first one is designing a modular architecture for web sensor retrieval systems to identify components and the way that they are linked together. The second step is accumulating components and successful patterns for integrating them into a functional search engine for a type of query. The final step is developing mechanisms to automate the process of composing search engines from a given type of query. In this article, we address the first step of the process, designing a modular architecture for web sensor retrieval system. In designing this architecture, we face 3 problems. The first problem is defining a set of components that are general enough to model different classes of web sensor retrieval systems, yet specific enough for researchers and developers. The second problem is ensuring the autonomy of these components. In other words, we need to design these components with explicit boundaries so that they can be developed independently. The third problem is ensuring the simplicity of developing these autonomous components. Our solution to these problems are as follows. We address the first problem with functional decomposition technique. We ensure the autonomy of components by designing them as services. We simplify the development of these components by providing a kernel shared among these services. These 3 solutions combine into a service-oriented, kernel-based solution for web sensor retrieval systems. Our contributions in this project include identifying common components of a web sensor retrieval system, modeling these components as services, designing a kernel underlying these services to simplify their development, and producing a functional search engine prototype based on our proposed service-oriented, kernel-based solution. Functional decomposition is the process of breaking down a software system into components based on activities that it carries out for its functionality. It involves identifying workflows or processes utilized by a software system and defining software components based on activities in these workflows. The next problem after defining components is ensuring their autonomy so that they can be developed independently by different researchers and developers. We address this problem by designing components as services. A service is an abstraction of an activity with a specific outcome. Each service is self-contained. To external parties, Each service acts as a black box. Various services can be composed to form a larger service. Services fit naturally to components in web sensor retrieval systems that we defined. First, each component in web sensor retrieval systems generated from functional decomposition process is an activity with a specific outcome. Second, by being self-contained as black boxes, services provide the autonomy that we need to facilitate independent development of components. Finally, the composability of services allows us to compose web sensor retrieval systems from components. Each component contains a set of functions to carry out a specific activity in the workflow of a web sensor retrieval system. To turn a component into an autonomous service, we introduce task dispatcher, message sender, and receiver running on a main processing thread. Task dispatcher is responsible for assigning worker threads to execute different functions. Message sender and receiver are responsible for interacting with other components to invoke services, as well as receiving service requests. Communication among components can be carried out by different means, such as in-memory pipes or HTTP. While this design of components as services solves the problem on autonomy, it complicates the development process. While researchers and developers only focus on functions in a component, they must also implement the complex mechanisms to serve those functions as services. Moreover, communications among components also require protocols, which introduce an additional layer of complexity. To address the complexity created by modeling components as services, we introduced the kernel. The kernel of web sensor retrieval system is a library underlying components. It provides mechanisms to operate a service. It handles the communication among services. It also provides abstract classes as templates for developing components of the web sensor retrieval system. The kernel is organized into three levels. The bottom level contains abstract classes that provide templates for components. These classes also contain mechanisms to operate and communicate between services. The middle level of the kernel contains utilities for starting up and setting the communication among services in a web sensor retrieval system. The top level of the kernel contains utilities that are commonly used by components such as HTTP clients and servers. Researchers and developers define their algorithms and mechanisms over the kernel based on the abstract classes defined in the level 0 of the kernel. This is the hierarchy of abstract classes defined in the kernel. The root of the hierarchy contains mechanisms for operating services and communicating among them. Leaves of the hierarchy are templates for different types of components that we defined from the functional decomposition process. To demonstrate the feasibility of our proposed solution, we developed a prototype for a web sensor retrieval system. In this prototype, all components are autonomous services which are developed independently from each other based on a shared kernel. These services are composed programmatically to form a functional search engine. The kernel and components of our prototype are implemented in Python. MongoDB provides indexing, storage, and matching mechanism for our prototype. To host sensors and data streams at web resources, we develop a Node.js-based Web of Things middleware called Web Sensor Platform (WSP). We replay sensor readings from Intel Lab dataset to simulate a sensing infrastructure. We deploy our middleware on both a Raspberry Pi 3 and a remote workstation to simulate a local and a remote sensor source. For client application, we utilize an off-the-shelf RESTful client application running on a tablet PC. These are screens captured from the client application. The query for sensors that capture apparent temperature in Celsius is written as a JSON document. The information of the matching sensor is also presented and returned as a JSON document. A key capability of our prototype is programmatic composition. We developed components independently from each other and then utilize the system utility in the level 1 of the kernel to find, start, and compose these components into a functional search engine. Presented on the slide is a part of the script that guides the composition of components into a functional search engine. The use of kernel produces significant reduction in development effort, measured in both number of functions and lines of code. On average, only 22% of the system, which corresponds to a specific mechanisms and algorithms to process a given type of query and sensor, must be developed. As more components are accumulated, this figure will reduce even further. Creating a search engine for any sensor and data stream in the Web of Things is an extensive, diverse, and challenging problem. Working together is the solution. Our service-oriented, kernel-based solution lays the foundation for working together. If we continue to advance algorithms and mechanisms for web sensor retrieval systems, if we continue to encapsulate these advancements into services, if we continue to share these services, then with our solution as the foundation, one day we will achieve a search engine for any sensor and data stream in the Web of Things. Thank you.